And that's where the space-time comes from, you know, when they, because of dark energy. I don't know. I don't know. Nobody knows. No one's going to know. But I do know this. Mass gobbles up space-time because of positive curvature in space-time, okay? And dark energy, listen, gravity isn't a force. It's curvature in space-time. Dark energy is not energy. It's negative, not a positive like gravity. It's negative curvature in space-time. And so instead of two galaxies, here's a galaxy and here's a galaxy, instead of them coming down like this, they diverge instead of converge. They go away. More space-time is created. It comes out of nowhere. I don't know where. You know, and you say that, you know, I can't see the Earth accelerating outward. I can't see. Well, when the clock or the ship, right? How he said he would have to, you know, he's going to follow the Earth if he doesn't accelerate, right? So he can accelerate at an exact acceleration that is opposite to the acceleration pulling him down, right? When I want you to think about it. You got Earth here, you got a rocket here, and he's staying right in the same spot. But you can see that he's got his thrusters on and he's accelerating. But do you see him moving? But we know he's accelerating because we see his rockets on. Nobody bats an eye when I say that. They're like, oh, that all makes sense. Well, then why, when I say the Earth is accelerating up and you can't see it, you're like, oh, that don't make no sense whatsoever. I don't see the rocket moving either, but I know he's accelerating as I see his damn rockets on. And I want to hit on this a little bit more here, this thing about moving. You have to be moving in curved space to actually stand still. It doesn't sound right? Yeah. It's like being on a hill, you know what I mean? And you have wheels on you're in a little cart and you have wheels. The only way you're not going to go follow the hill, you know, the geodesic, the only way that you're not going to follow that hill and slide down the hill, right, is if you're actually accelerating up at the same rate that gravity is accelerating you down the hill, right? If you could have a magical rocket behind you, right, that just accelerated you to overcome that, but not overcome friction, you know what I mean, so that it would start going up the hill, then you would never fall down the hill. Even if the hill was like really, really steep, you could just stay right here, right? If you had a rocket that was accelerating you up at the same rate you're accelerating down, right? So we can say you can't be on a hill like that when you have wheels unless you're accelerating. Unless you're accelerating, you can't be standing still, right? You can't be standing still unless you're accelerating, overcoming this acceleration down, right? You have to constantly be. Now, can you see it though? If you have rockets and you're accelerating exactly the same amount that you're accelerating down to the Earth, can you see that you could be on, like you could have a hill almost like up and down and still be standing there, but you can't do that unless you can't stand still on that hill unless you're accelerating to overcome the acceleration of the gravity, to overcome the geodesic of the hill, right? So, anytime you're in curved space-time, right, it's going to be because of some large mass that you're being drawn towards, right? So you can understand. That's what, you know, like when you have, like, you might be thinking, well, the space station, they don't have rockets on constantly and they're not falling to the Earth. No. In all thought experiments, you take out all the equations. You know, that's why you always go down to a two-dimensional thing. You want to go down to the simplest form and take out all the others, because if your ball drops, if it just stays in the same plane, you know what I mean, just drops down, why flood your information thing with the other two dimensions? You know what I mean? You only have to care about this one plane, the x-axis, you know what I mean? If the ball goes in the y-axis, why even bring it up? Why, you take it down to the simplest whatever, man. So you always take out those kind of things. So when you're talking about the Earth and something floating on top of it. We're talking about everything just moving at the same velocity, which would be the same as standing still. So everyone's standing still in scenarios, you know what I mean? And so when we talk about the Earth and you're putting a clock here or something, yeah, it would go straight down, and no air, it just goes straight down. Why doesn't the USA whatever? Because they are going so fast. It's like throwing a ball, right? If I throw a ball, right, it's going to come down like a parabola. What if I throw it harder? It'll come down with a parabola, down further. What if I do it again and again? I make my parabola bigger and bigger by throwing it faster and faster, right? Sooner or later, when it comes down, that parabola is going to miss the Earth, right? It's just going to drop. If I can do it fast enough so that it goes away from the Earth at the same rate that it falls, then it'll just basically keep falling, and you know what I mean, missing the Earth, and then just orbiting. It just ends up orbiting if you get it at a perfect, angle and everything or whatever. So that's why, when we talk about a spaceship, now if it wasn't moving left to right, and you just popped him in there above the Earth, he would just literally, without air, he would go literally straight down to the Earth. So, you know what I mean? Which I also wanted to bring up too was, now I want you to think about this in 3D, right? Because these people think that like the curved space-time model and the flow or river space-time model are different models. Okay, they're literally the same exact model. Okay, it's just the curved model we present in a 2D graph, right? And we have time graphed onto that two-dimensional plane, right? When we show it, right? We show our little geodesic going down. Here's the apple. Here it goes down. All right. And the other one, the river flow model, right? I'll call it the river model. The river model, right? It is the same exact thing, but it's in 3 dimensions, right? Because it's on video, and there's no time dimension. When you see that geodesic that we show, that's in the time dimension. So if you have a video of it, you don't see that. You don't see that geodesic, right? It's taken out, right? So that's the difference. See, now if I take my 2D model, right, with this geodesic, right? Let's say I have an apple here, and I'm saying it's following the geodesic down and falls onto the Earth. Let's say we do a video of that. Now, what does it look like? You'd have the apple right here, right? And it would just fall straight down. You'd have a straight line. There would be no the geodesic, which is a straight line in curved space. We would see it. We see it as a straight from Earth, from that frame of reference. We see it as a straight line. You're just going straight through, right down. You're just coming right down to the planet from the Earth's frame of reference. But I want you to imagine this, right? Imagine you have an Earth, right? And I put a whole bunch of balls, and I surround and we're going to do a 2D one. I'd surround the Earth with balls, and they're all floating there, so they're all going to fall, right? And they're going to follow that geodesic. Now let's say in 2D, I draw all the you can see the Earth and you can see the balls I drew. I'm going to draw a 2D geodesic going to the planet, right? And you'll see all the balls, right? And you'll see this kind of thingy in 2D, right? But you don't see that. What if I animated that now, right? Now all the balls have a straight line straight to Earth. All of them. Yeah, they're all flowing into Earth. Dumbasses. And if it was 3D and animated, it would look like a river. It would just like, you know what I mean? The balls would just go into, let's say I put the balls out a lot far away. All the balls would just go, they would all flow like a river into the earth. It's just a 2D model where you see the time axis, you know, in the one model. But if you plot everything from that into the 3D thing and you did a video, you get the same, they would look exactly the same. And if you take the river model, right, and you plot, you just take one dimension, right, just one dimension, and you plot it on a 2D chart that has time and distance, guess what? You'll get a little thingy that looks like the geodesic that we always draw on the thing. It's the same exact model. It is different. It's just literally if you plot the everything and transfer it, the river model looks exactly like the curved model, and the curved model looks exactly like the river model. No one sees this? Like, really? Am I the only one that sees it? Why you think that space-time itself is accelerating? If space-time itself wasn't accelerating towards the Earth, then that means that the man falling would be accelerating towards the Earth, right? But we know for a fact that he is not. He's in an inertial frame because all the math and experiments prove that. If he, you know, if we put him in a box while he's falling, he could do all experiments that he could possibly think, and none of them will say that he's accelerating. They'll all say he's in an inertial frame. Plus, we know that when he's falling, all the clocks around him, if they're falling at the same rate, like they're in the same frame of reference as the falling guy, all the clocks are ticking at the same time, even if they're inside this fictitious gravitational force, you know what I mean, field. Time gradient does not cause gravity. Space-time curvature does. Time gradient can't cause gravity because there is no time gradient unless you're attached to the Earth or you're accelerating at the same rate. Because a falling object is inertial. So all the clocks in his frame, okay, they can't be changing. They have to be ticking at the same time because inertial frames, by definition, have the simplest physics laws. And time dilation is not simple. If everything floats, you're inertial. That's it. End of sentence. I want you to realize, I've never heard anyone say this. I don't know why, because it looks like it's so obvious. What is acceleration? I want you to think about it. If you got this is the x-axis, this is the y-axis. This is north and east. If you accelerate east, yeah, you're accelerating east. If you go up, you're accelerating north. What if you go at a diagonal? If you go at a diagonal, you're accelerating north and you're accelerating east. You see what I'm saying? My whole point, did you get it? Time is just a spatial dimension that we cannot see, right? So if you're accelerating through space, you're also accelerating through time, right? So what is time dilation? It's just that mathematical thing that we do so that we can take account for that thing, that you are accelerating through time. So when you accelerate through time, that means time is accelerated. Get it? That's all it is. That's all time dilation is. It's a mathematical equation that you throw in with your other equation, right? So that it'll take into account the fact that you are accelerating through the time dimension, right? That's all time dilation is. I've never heard anyone say that, but that's all it is. This brings me to my last thing. You know, when they say that we're going accelerating, or you're going in a really, really fast, you're almost speed of light, you know, the clocks in front of you, even though they're not attached to you, will be, you know, the further in front of you, the faster the clocks will tick, and as you go backwards, you know, they'll tick slower and slower as you go back. Is this true? Because that's what they were saying about the Earth, but I find out that no, that isn't true. If there's no gravitational field, you are not falling, man. You are not. Your clocks are all the same. So is this just an illusion, or are they just lying, or what's the deal with this, man?